Welcome to another Juddy Productions video, this time looking at VCE physics, and the focus of this particular video is radiation dosage. Looking at the screen at the moment, we see a range of different ways in which we can be exposed to radiation. So you can see that medical is actually the highest form of radiation exposure we have, going all the way down to atmospheric weapons testing and everything in between. But today's video is more about actually performing calculations of radiation dosage. So first of all, let's have a look at how radiation affects the human body. This is an amazing picture, this one. It presents the complexity of calculating the impact of radiation upon the human body. First of all, we can see background radiation is something to consider. The fact that we are exposed to radiation, that is ionizing radiation all the time, and it comes from a range of different sources, as you can see. Next, this graphic shows us how to compare exposures, and we can see that something as small as a dental x-ray has very small radiation dosage, all the way up to receiving something like 10 sieverts, which is fatal within weeks. We'll be looking at units like grays and sieverts shortly in this video as well. We then focus on the symptoms of radiation exposure, and you can see that there are some short early onset symptoms, such as nausea, vomiting, diarrhea, headache, fever, and then there's also long-term or later symptoms. Finally, this graphic also looks at the chances of death based on exposure. So this particular graph shows that when you're only exposed to 1 to 2 sieverts, there's a very small chance that you're going to die as a result. Whereas when you increase the dosage to 2 to 6, 6 to 8, and then in fact from 8 and above, once you get to around 10 sieverts, there's 100% certainty of death. It's quite a large exposure dosage. So let's look at some appropriate terminology we use when looking at radiation dosage. First of all, we have the absorbed dose. And in simple terms, it's the energy deposited in a kilogram of substance by the radiation. Next, we have the equivalent dose. Not all forms of radiation interact with biological tissue the same. The equivalent dose is the absorbed dose weighted for harmful effects of different radiations. So for example, alpha, beta, and gamma all interact with biological tissue in a different way, to a different extent. So to calculate the equivalent dose, we take the absorbed dose and we multiply it by a radiation weighting factor, WR. Then finally, effective dose. Not every region of the body absorbs radiation to the same extent. So an effective dose is a way of comparing how, for example, your stomach will react to radiation compared to your liver, compared to your brain, compared to your kidneys, etc. And the effective dose weights the equivalent dose for susceptibility to harm of different tissues. So to get the effective dose, we take an equivalent dose and we multiply it by the tissue weighting factor, WT. Now the questions we're about to look at will all involve absorbed dose, equivalent dose, and effective dose. Example number 1. A stomach of mass 1.8 kilograms is exposed to 0.9 joules of alpha radiation. Task 1, calculate the absorbed dose of radiation. So here's our image. We can see a person's stomach and we can see an alpha particle representing the alpha radiation. Recall, absorbed dose is the energy deposited in a kilogram of substance by the radiation. So D is the symbol for absorbed dose, that's what we're trying to calculate. ER is the energy of the radiation, and that was 0.9 of a joule. The mass of the stomach, or our target, is 1.8 kilograms. And here's the equation to work out the absorbed dose. It's simply the energy of the radiation divided by the mass. So that's 0.9 of a joule divided by 1.8 kilograms. And that gives us an absorbed dose of 0.5 of a gray, where 1 gray is equal to a joule per kilogram. Task number 2, we now need to calculate the equivalent dose of radiation. Remembering this takes into consideration how much biological damage or hazard the various forms of radiation provide. So the equivalent dose, absorbed dose weighted for harmful effects of different radiations. So H is a symbol for equivalent dose, and I think of H for harm. D, the absorbed dose, was 0.5 of gray, and that's from our previous question. And we can now look at the weighting factors for the various forms of radiation. And we can see that an alpha particle has a weighting factor, or a weighting radiation factor of 20. That is, it does 20 times more damage or harm to biological matter. So to calculate the equivalent dose in radiation, we take the absorbed dose and we multiply that by the radiation weighting factor. In this case, for alpha particles, that is 20. So we have a 0.5 times 20. So in this example, the equivalent dose of radiation is 10 sieverts. And that goes from a unit of gray to now a unit of sievert. Takes into consideration the radiation weighting factor. Finally, number 3, calculate the effective dose of radiation. This will take into consideration the fact that it's the stomach being radiated and not other organs within the body. So effective dose. It is the equivalent dose weighted for susceptibility to harm of different tissues. So our symbol is E for the effective dose. Our equivalent dose was 10 sieverts from our previous calculation. And now we want to look at our tissue weighting factor for the stomach, and we can see that that has a value of 0.12. It effectively means it is impacted upon or absorbs 12% of the available radiation. So the tissue weighting factor for the stomach is 0.12. So to work out the effective dose radiation, we simply have to take the sum of all equivalent radiation multiplied by the tissue weighting factor. So in this case, it's just a case of 10 sieverts, that is the equivalent radiation, multiplied by a tissue weighting factor of 0.12, representing 12%. And that gives us a value of 1.2 sieverts. So effectively, of the 10 sieverts from the equivalent dose of radiation, only 1.2 of it is impacting upon the stomach. Example number 2, a patient has a positron emission tomography PET scan, a PET scan, on her brain using the radioisotope fluorine-18. Fluorine-18 emits beta plus particles. Once the scan is complete, the radioisotope leaves the patient's body via the kidney and bladder. In this process, the following equivalent doses are received. So we can see the brain receives an equivalent dose of 16 millisieverts, and in the process of expelling the isotope, the kidneys are exposed to 12 millisieverts and the bladder exposed to 12 millisieverts as well. So the task is to use the tissue weighting factor provided to determine the total effective dose absorbed by the patient in their brain, kidney, and bladder. So we'll use the two tables to the right. Obviously, the total effective dose will be the sum of the individual effective doses impacting upon the brain, the kidney, and the bladder. So we represent summation, or the sum of, with the sigma symbol, the capital sigma. So let's have a look how we calculate this. We're going to work out the individual effective doses of the brain, kidney, and the bladder. So step 1, let's work out the effective dose upon the brain. So we can see the brain has an equivalent dose, H, of 16 millisieverts, or 16 by 10 to the negative 3, and it also has a tissue weighting factor of 0.1, meaning that only 1% of that radiation impacts upon the brain. So when we multiply those two together, we find the effective dose of radiation to the brain to be 1.6 by 10 to the negative 4 sieverts. That's the contribution to the overall total effective dose of these three organs. Step 2, let's repeat this for the kidneys. So the kidney has an equivalent dose H of 12 millisieverts, or 12 by 10 to the negative 3 sieverts. The kidney has a tissue weighting factor of 0.009, which is like 0.9% of the radiation is absorbed. And so we're going to work out the effective dose upon the kidney. We multiply the equivalent dose and the tissue weighting factor, and that gives us an effective dose of 1.08 by 10 to the negative 4 sieverts. So that's the effective dose absorbed by the kidneys. Finally, we want to do the same for the bladder. So it has an equivalent dose of 12 millisieverts, or 12 by 10 to the negative 3 sieverts, and it has a tissue weighting factor of 0.04, or 4%. So of the 12 millisieverts, only 4% impacts upon the bladder, or is absorbed by the bladder. So that gives us a value of 4.8 by 10 to the negative 4 sieverts. So now we have the three individual effective doses. So to work out the total effective dose of the brain, kidney, and bladder, we need to sum those values together. So it's 1.6 by 10 to the negative 4 for the brain, plus 1.08 by 10 to the negative 4 for the kidney, plus 4.8 by 10 to the negative 4 for the bladder. We add that together, and our total effective dose for this particular exposure will be 7.48 by 10 to the negative 4 sieverts, or 0.748 millisieverts.